You may have to create a sandbox, which is the area which we're coding in. So when you go to, I'll find you the link. Well, we'll give a couple of minutes to see if we get any zoomies. Good morning, Ritu.
Good morning. How are you, Steve?
I'm good today, thanks. And how are you?
Yeah, thank you. Good.
Well, we'll just wait for maybe a couple of minutes. Maybe we get another zoomie.
Yeah, sure. Will do.
If you could all just sign in, that would be good. I started to upload yesterday's link. Sorry, the video of yesterday up into Dr. Rice's YouTube channel. But as you can see, there's no issues found. So we can go on to the next step, which is to make that publicly available and publish. So that's yesterday's session in the channel.
Do you mean on the YouTube?
Yep.
Okay, thank you.
There it is. Dr. Rice has asked me to upload it at the end of every day. But I do it in the mornings because it seems to take, well, it's a 2.5 hour video sort of, and it takes a long while for them to do the checks, like half an hour it took just then. So I will do it first thing in the morning for the day before rather than try and do it at the end of the day.
Okay.
I didn't know how long it was going to take because yesterday it took an hour and then just stopped. So I don't know what processing HD version means, but it's there and it's public. Oh, we'll get rid of this draft one there. That was the one I created last night and it just stopped. So I'm going to have to get rid of that. Be very, very careful which ones you delete. I don't think you'd be happy with me if I deleted all these videos. Well, let's go back. There we have it. Okay, so I think we should probably make a start. Did you sign in, Zaid? Yeah. Yeah, I can't see you on the. You are in the chat. You're in the call. Oh, okay. Right. Okay. So let's activate our sandbox at this point, and hopefully we won't have to go back and redo everything again. Oh no. I have to identify myself by phone. It's a pain. Only happens to me. It's because I'm inside this system, I think. Yeah, we all have a two-step verification. It's built into it's a security thing, isn't it? Drives you crazy. I'm going to leave that. And then I normally can't remember my phone number, but I've typed it in enough times now. It's I think I might. You're 819633. Good plan. I'm in. Okay, let's begin. Oh, look, masks. Excellent. BCU masks, even better. Huh. Okay, so let's begin. So what do we do if we have missing data? Now, before when we have missing data, we just deleted the row. Okay, but that maybe isn't the best thing to do, especially if you haven't got that many rows. So we're going to look at firstly how you can and what you can do about missing data, which isn't just deleting the rows. Okay, so the code is asking us, as usual, to import pandas as PD and install missing NO. So that is a package that's available that can deal with missing data. And, sorry? Well, pip is an installation package. So if it's well, we could install missing number and then import it as something or other. It's available to us directly. Yeah. Okay. So other way around. So then we load the GitHubs that have got as before. It's got go along here. That is our Titanic CSV data set. So it gives us all of the data about the people that were on the Titanic. We're looking about survivability of being on the Titanic. Understanding probability would have been a good start. Then imports, well, not imports, it gets the GitHub, which has our nice little graphing program on. It enables us to do a couple of 2D scatter plots, for example, or a surface plot, which is a 3D plot. We've done both of those. And the other thing is, it's so small, the screen drives you crazy. Yeah. And so then we do as we did before, we load our CSV file, Titanic CSV, looking for the whether or not they survived, which is our result, if you like, and that's our separator, and the headers, i.e. the names of the columns, they're in row 0. So quick look at the data again. We'll see the first 5 elements if we run this just as a check. The head will show us the first 5 parts of that array, of that table. So let's go down, have a quick look. Go down a bit. And eventually, what went wrong here? Head should have showed us that. Oh, maybe it's down below. Yeah. Okay, so these are our first 5 people that in the Titanic data set. And as you can see, if we look at row 0, that the cabin is not known. So that is not a number. So we can't deal with that, meaning unknown or missing data, or data it can't process anyway. And then we have what class they were in, whether or not they survived, which is a Boolean, obviously a 1 or 0. No values can be there. And we have to work out what we're looking for is a regression on whether or not they survived. Okay, so we have to find what combination of factors allowed them to survive. So the next stop now is to have a look at how many samples we have. So to find out the shape of an array, you simply just use the dot shape function. Dot shape function for any array will tell you what shape it is, and that will tell us how many rows and how many columns. And we've got 891 rows and 12 columns. Okay, it's quite handy, that dot shape. It helps you to, for example, if you want to copy one kind of array to another one, it helps you with what dimensions you're dealing with to be able to, and it's a good check also that you're creating the right size data storage area and the right dimensions of data storage area when you're moving data around. So it's quite a powerful idea. So we've got data, 891 passengers, each described by 12 different variables. Okay. Do we have a complete data set? No. We know from history that there are more than 2,000 people on the Titanic. So we know straight away we're missing information of more than 1,000 people. But the question is that missing information important? For example, if you already know what floor somebody was on, did it really help to know what the cabin number was? Not really. It's not really going to give you a great deal more information. So in fact, even though a lot of the cabin number information is missing, that may not be a problem for us. If other, sorry? Yeah, but we haven't actually, we don't have that information. We have just the number. You're absolutely right. If it was, whether, for example, the cabin was facing the sea or facing the inside or had no windows at all, then yeah, that would be, if we had a further key that says range cabin, this has this, and then you could go down. But all we have is the cabin number. So at the minute, I don't think that's going to be a problem that we don't have that information. Let's see what other information we don't have and see if it's going to be a problem for us. So how can we tell what is left is complete? Now, we can look to see, we could print the entire data set, but that would take a long, long time. Or we can use pandas to report the columns that have empty cells, that have NaN values, okay? And that's what that function down below does. This function here is null on the data set, and we're summing them for the whole frame, and we're then compiling this missing data list. So this will give us the number of missing entries per column. So we should get column, number of missing entries side by side, and we can rename that column holding the sum, call that empty cells, which is going to be quite useful to us, and then print the results. So let's just load that in, run that, and there we have it. We've got something called empty cells, and this column called empty cells, and these are the number of empty cells. And as we can see, the biggest issues here are the cabin number and age. Age might be more relevant than cabin number, but for the rest of it, we've actually pretty much got a complete set of data. That's what it looks like. So we don't know the age of 177 passengers, nor where 2 of them even embarked, and the cabin information for a whopping 687 persons is missing. So we can visualize this. Sometimes it can be helpful to visualize where the missing data forms some kind of pattern. Here's a few ways that we can plot the absence data. One of the most helpful is to literally plot gaps in the data set. Okay, so let's have a look at this. So that's what this importing missing number as MSNO. So that's the point you made. You don't have to import it until you use it, really. It's kind of good practice to import it a bit higher up, as you said, because what's useful then is that if you want to create another version of the program, you could just cut and paste your import section, bring it over, and then carry on. Whereas if you've not imported it until later on, and you've tried to use it with a cut and paste, it will tell you, don't know about that, don't know what that is. So it's a good idea to keep all of them right at the top. So again, we've got a matrix chart, and that's here, MSNO, which is our missing number. And it can do a matrix chart on our data set using a figure size 10 and a font size 5. It's quite small. Sorry, figure size 10. Okay, that's in either direction. And the font size is 11, which is reasonable. So let's execute it, see what it looks like. Oh yeah, this is how far as we got yesterday, I think, to show where the missing data is. It's quite a nice visual there. So where it's missing is white. And you can see quite a lot are missing. The white bars in the graph show where data is missing. Here the patterns aren't clear visually, but it could be that many passengers missing age information are also missing cabin information. Yeah, maybe they just didn't have the availability of their ticket. So if their ticket wasn't kept, if it was lost, I mean, when you went on board, they would have taken half of your ticket, kept half of your ticket, so that for fire drills and things like that, they knew where people were on board and not. But if a box load of those tickets was lost, then that might have been what happened here. So we lost a lot of information both on the age and cabin, because if you think about it, that's the kind of information that might have been on the ticket, purely from the point of view of the manifest. Might have been partially lost. So omitting cabin information, identifying individual passengers within information. So now we're going to look at which passengers themselves with unknown age, and we're going to use is null on the rows, but with no value. So it's unknown age is a data set. We print only the columns we want for the moment to better fit the screen. So we're going to limit the output to 28 rows, and that's what this is, sorry, 20 rows, and that's what this final number here is. So to do 420. So we're going to print using our passenger ID as a key. We are going to get the name, survived, and age. Let's have a look, see what happens. So there's our passenger ID. That's what we started with for all our passengers. And this is all the columns where age was a null value. Okay, so that's the point here. The age was a null value. We didn't know their age. And to me, it doesn't look like that was important about whether they survived, because it looks like about half of them did, which is interesting because that is not quite representative, is it? Because not half of them did survive. So this technique can be used to list the passengers with missing cabin or embarked information as well. So we can use it with a logical AND clause to see how many passengers are missing both cabin and age. So if we look in here, we'll see missing age is data set looking for age is null. Missing cabin, data set looking for cabin is null. And now we can logically combine them. We can say unknown age in cabin is data set missing age, and, as in logical and, missing cabin. Now what that means is, if this will show up the list of passengers that had a missing age and also a missing cabin. So the intersect of the two, the and function, logical and, not plus, but and. Doesn't mean plus, because if it did that, you would end up with the numbers of both. And you can't, this is a logical function here. This and function is not a plus. So we're printing a number of passengers with missing age and cabin information, and giving the length of that as well. So that's the length. We have to print, well, normally you have to print how many you're going to print of something, and it's the length of actually that and there. So let's run it. So the number of passengers of missing age and cabin information is 158. Okay. So what that's saying is, it's quite clever. It's using the length of this list to give us the number. Because if we actually just print the list itself, we would get 158 rows. In fact, let's do that. Let's just chuck it in there. Just simply print. Sorry, not even that. Just simply state it, and it will print it as a table, hopefully. So we have got here. Yeah, that would do it. Yeah, that would do it. Or we can just type this, can't we? We can just type unknown. Is that an underscore? Unknown age and cabin. Spell it correctly. Unknown age and cabin. And it should print us a nice table, hopefully. Oops. Sorry, it's underscore, isn't it? Underscore age and underscore cabin. Let's go with that. I chucked in an error here. Age unknown, age and cabin.
Steve?
Yeah.
I think there might be underscore at the end if you remove that.
Yeah, that's what I've done. Yep, you're right. Try again. Okay, so now we've got 158 rows and 12 columns as we expect, and it's just simply done the usual thing, which when you type the name of the table, you get the first 5 entries, the head, and the last 5 entries, the tail. And there are 105 entries altogether, 158 entries altogether, which lines up with what our using the length function here has done for us. Okay, let's move on. So we can get a lot of information from a table, but create new tables. So our suspicions are correct. Most passengers missing age information are also missing cabin information. Normally from here, we would want to know why we have this issue, and a good hypothesis is that the information was not collected well for the passengers with the cheap tickets. Yeah, I'll go with that. Let's plot a histogram of ticket classes and another of just people missing information. So what we're investigating now is whether or not people with cheap tickets were the ones with the missing information. That's interesting. possibly it could be that people with the more expensive tickets had room service, for example, and there would have been a record possibly of people using a room service or a servant's an ironing service or something like that, whereas the people in the cheapest tickets would certainly not have done that. So maybe they just simply didn't make a very big footprint in their journey. So let's look at this. Graphing is a custom code we use to make the graphs quickly. We know that. If you'd like to read it and detail it, you can find it in the GitHub. So this is going to give us a histogram of our data set for passenger class. And the title of it is ticket class for all passengers. And we're going to show every one that is true in terms of is that information available? And then another one using missing cabin. And let's see. So we can compare the one of ticket classes, which is this one for all passengers. There's our histogram of the class. Of course, 1.5 doesn't make any sense in terms of passenger class, which is interesting. And then with the cabin. So yeah, we can see there quite clearly that people with the lower classes were most likely to have missing data. So these are the different ways that we can examine data. So we can, it seems that those missing information typically with passengers with cheaper tickets, these sort of biases might cause problems in a real world analysis. So what you can then do is probably have two models running, one for classes 1 and 2 and one for class 3. And in fact, below that, they even had something called steerage, which means that you were in the bowels, basically. Okay, so what we need to do is to normalize that over the number of passengers in total. Yeah. But if you think about it, they all suffer the same normalization. You know, the number in class 1 would be the number in class 1 divided by 2,000 passengers, and so on by 2,000, so on. They'd all be divided by the same thing. So, if you like, any number that you have is equally valid because you will be dividing. If you were trying to work a probability out, you divide it by the same number. I see what you're saying. I can understand where you're coming from, but in reality, you just end up making everything smaller. That's the, yeah. But yeah. So the count in class 1s that were missing, cabin and age information, was these. This is the point that you made is a very interesting one, and it's a very big area in research of what do you do in classification if you've got an unbalanced class, if you've got more in one class than you have in the other. And there are lots of techniques around, and I'll put some files up in the files about how you do it. And really, it's usually involves in intelligent sampling, so that you still keep the same variation, but you just have less samples. Or you can go the other way, which is to take your existing samples and create other samples that have got the same profile and characteristics of the original. So you can either decrease the big sets or increase the small sets in order to unbalance them. That's a very simplified view, but basically that's what you can do. But we've not yet got to that here. We will get to it because it's important to have your samples as being representative. That's the key phrase. Is your data set that you're working with representative? But we're asking for absolute information here, not necessarily. I mean, if you look at it, it's 7 times as much. And I don't think there are 7 times as much third class passengers than there are first class. The point is that it's a valid point, but you can't just simply numerically divide one by the other, because you have to look at the importance of the ones that you're deleting or the ones that you're balancing. And hopefully we'll get onto that. So missing as 0, it seems that those missing information typically were passengers with cheaper tickets. These biases may cause problems. So what we're going to do is another issue to watch for is that some data sets may have missing values appearing as 0, while a Titanic data set doesn't have this problem. Let's see what would happen if we had been the case. So what we're going to do here is we're printing out the average using, now numpys are is a Python numerical package. It's very powerful for doing all sorts of statistics, the simplest of which is the mean. So it's calculating the mean of all of the ages. Okay, so the mean age is the NP mean applied to the data set dot age. So that's the subfield of the data set table. And then print the average age on the ship was. And now make another model where the missing ages contained a 0. So we're going to make another data set now. So data set age of 2 is data set age 1 and dot fill NA. That means where it found a 0 value. So we're going to fill in with zeros the line with the average of the average age called age 2. And then we're recalculating the mean age based on that. So what we're doing is we're filling some rows with zeros and then recalculating it and see what effect it has. So the average age on the ship was 29. And then if we fill a line with zeros, we'll end up with that it's actually reduced the overall age. So therefore, you have to be a little bit careful. Let's see what that looks like now. So let's see if we can see it. So in here.
Steve, sorry, I'm having network problems, so I was disconnected.
Okay, no problem. No problem. So let's just type mean age. Oops, didn't mean that. I meant that. And we've got our mean age here. That's the new one that we've calculated. So I want to find. Let's just see what the data set is looking like now. See if because we might not be able to see that row that we put zeros in. Where did we put zeros? Yeah, there's zeros here. Let's go down and have a look. Let's see what we found. Yeah, I'm just trying to find out where, because what it's done is where there was a 0, it's putting in the mean age. That's what we did. Obviously, unfortunately, I can only see the first few rows.
Do we know the passenger ID?
Have you found one? Which one is it? Number 7. Oh, I don't see number 7. Oh, you print the whole thing. Oh, okay. So you've got the first 50. And number 7 did have a 0 in, but it's now got the average age in. Age 2 is 0. Yeah, all hours are high. Oh, 888, there's one. Yeah, you're absolutely right. We found 881. Yeah. Yeah, so if we put in, so that shows you how you can reveal biases in the data. So what's happened here? So we've considered the values of 0 not to be missing, but rather to be actual ages. This goes to show that it can be important to time looking at raw data and running analysis. Another fast way to get a feel for a data set is to graph how it's distributed. So again, we can look here quite simply of our histogram, which tells you how age 2 from 0 to 80 is distributed. These are our, if you like, this is our ones taking into account the 0 values, and immediately you've got somebody at age 0, so a newborn baby, is over 200, which of course is not a sensible thing to do. It's not a sensible thing to do. That clearly doesn't reflect the real situation. You'd have to, so you can't really ignore them. That's the thing. You have to do something with them. So let's look now about how we can really handle missing data. So we've seen the effect of missing data. We've seen the effect of simply putting that missing data to a value 0. That didn't work exceptionally well. So we're going to look now and see how we can more intelligently handle missing data. So in this case, we know an unlikely number of very young children. This was called a further inspection of the data, and hopefully help us spot that missing ages appear as zeros. Now, if we saw that ourselves, we would immediately suspect that that's what had happened. So there are many ways to address missing data, with pros and cons for each. One of the ones we looked at, the less complicated, is what we used during the studio and also the designer in the data transformation, was that we simply deleted the data with a missing row. We deleted the entire row, took it out of our sample completely. So when we have a model that can't handle missing data, the most prudent thing to do is to remove the rows, the information missing. So let's remove data from the embarked column, which only has 2 rows with missing data. So we're going to create a clean data set where we cumulatively fix missing values. So we start by removing rows only where embarked has no values. Okay. So the original size of our data set was data set shape, which gives us 700 and whatever it was by 12. And the clean data set is the data set using this function drop NA for the subset embarked. So for our embarked subset within the main data set, we see we're going to simply remove any row that has NA in it. No data, has no data in it. And then our clean data set is that we re-index it. So whereas our numbers went from 1 to 72, because we are 732, because we are permanently deleting a record here, a line, then we have to simply renumber all of the other lines, all of the other indexes. They have to be renumbered. That's important because later on you might want to look at an average over a range of values. And if you have not re-indexed it, then you could run into trouble because you could hit a missing value quite easily in your range, and your program wouldn't like that at all. So, and then it then shows us then the shape finally of how many we have once they're removed. Now we think there's only 2. So really the difference between our final shape and our initial shape should be 2. So let's see. So our initial shape was 891. We've taken out 2 rows and we've got 889. Notice that age 2 is still in there because we've got 13 rows, sorry, 13 columns here. So that's what we've been able to do. It's a bit clumsy and it may not, well, it's simple, but it may not be a very good thing to do. The next thing we can do is to possibly replace empty values with a mean or median for that data. That kind of makes sense. Replace it with the average. Not sure that's going to be the very, very best because, sorry? Yeah, what we're going to do is we've got missing values and we've tried a couple of things. We've tried setting the missing values to 0, huge distortion bias for the younger students. We've tried doing what we did before, which is to remove the rows. But again, we only get, that's not great because there clearly is a real number. And if you remove the row, you might have removed some very important information. Certainly information that is discriminative, maybe not that one because you're removing disembark, but all of the other values may be really important. And by taking out the row, you take out that important data. And if you've got a limited data set to start with, if you start taking out rows like that, then your data set is going to get less and less representative, especially if that embarked equals not known stuff also related to something else, because then you've actually skewed the data twice. You skewed the data by not having an embark value, and you skewed the data again by taking out more important stuff. Oh, that's a huge question. Yeah, it's huge. It all depends on the number of classes that there are in total. It also depends on the method. Some methods require a lot more samples. In general, the more samples you've got, the better, if it's live, because you stand more chance of bringing in outliers, because an outlier won't just be out there somewhere. There'll be values going towards it and away from it. And if it's a genuine outlier, it will be way out there because there's a lot of samples. So if you're doing clustering, for example, a big decision you have to make is that data sample part of a cluster or a real outlier? And at what point does a cluster actually get defined in terms of the diameter of the cluster for the features? And they're 2 huge research questions. And there's all sorts of different approaches. One approach is, for example, to look at the density, how well packed they are, and to say, well, if they're not well packed, then it's starting to become further and further away, and then maybe into another cluster which will be more densely packed. I'm thinking at the moment of applying some physics concepts to decide whether something should be connected together. I'm looking at the idea of escape velocity. So I'm thinking of it in terms of gravity, pulling things in together based on the discriminative information. So yeah, that will come to that when we come to clustering. So replace empty values with the mean or median for that data. Now, let's say that you've got the value is increasing generally. And if you replace the data that's missing, so you've got a good value here, a good value there, and the one in the middle is missing, does it make sense to put in the middle the mean of the whole of the row? That's what we were just about to do now. Probably it makes sense to replace it with the mean of the ones either side of it, rather than the whole row. So that's what we're going to do now. Firstly, we're going to look at the whole row, and then we're going to say, well, is that really the best thing we could do? Maybe we should think that the changes are local and we should average locally rather than over the whole row. But let's see if that's where we're going with it. So we're going to replace our empty values with the mean or median for that data. Again, we're going to use numpys. So the mean age is the clean data set age.mean. So we can find the mean of that data set, of that field of that data set, the age field, and the mean age is that. And then we can replace the empty values with the mean. So we're going to clean our clean data set, which is our scratch pad, if you like. We're going to fill the NA values with this mean age, and that's a Boolean that controls the fill. So let's see what the data set looks like now. So we're going to print the clean data set. So that is the cumulative sum of the null values. And we're going to rename that column empty cells. So let's try and see where we go. So we've got empty cells, that's where we're starting. The mean age is here. If we now look at our passenger ID, we've got our cabin is 71. So what we're saying now is that we've got no empty values now for age. Why? Because we filled any missing values with the mean. Okay, so this is a kind of looking at the status. So we're going to check that that has actually happened, that we've actually made that move. And as you, I'm sorry. Yeah. That's right. Well, what we're doing is we're moving forward and cleaning the data set. I don't think we're going to stop here. I think maybe we'll. We are going to stop here. All right. As you can see, the cabin field is categorized a categorical field because there is a finite number of possible options for the cabins in our Titanic. Unfortunately, many records have no cabin listed. So for this exercise, it makes perfect sense to create an unknown category and assign it to the cases where the cabin is unknown. So that is helpful information to do that, to create this other. So we've got our clean data set of cabin is to fill the unknown values, fill it with so that they're known values, so it doesn't give problems to the system. And then we're going to print on the clean data set the null values all summed together to create this empty list. So let's see how that works. So here we go. There's our empty cells. And as you can see, there is now no missing values anywhere in the data set. We've assigned them. We've assigned them to either 0 or we've assigned them to the mean, the age, for example, as the mean. It makes no sense to get the mean of the cabin number. Nonsense. But the mean of the age kind of makes sense. It's not crazy. We just chuck zeros in. we said we don't know it. Let's assume it's 0. We're never going to do anything mathematical on cabin numbers. We're never going to average cabin numbers. We're never going to subtract them or do anything with NumPy on them. So really, and the system will crash if you put in not a number into it. A lot of well, you can't just remove cabin. Oh, I mean, so add from the whole thing. Can't do that yet. A bit drastic, because it might have some significance with further investigations. But what we do know is it doesn't have a mathematical one. It might have a categorical one. You know, for example, later on in the stage, we might realise that all of the room numbers that started with a 6 were at the very lowest level. All the ones that started with a 1 were at a much higher level. So also you could find that all the numbers that ended with a particular number might have been double, triple, or quadruple cabins, where a lot more people might have died all at once. That kind of further information might be available from the design. It doesn't have to be the passenger manifest. It can be from the design of the ship. You know, you could put that kind of information in. But what you're never going to do is to subtract cabin numbers or might find the mean of them. So in terms of making the thing work, it kind of makes sense to put them to 0, things you don't know, because the number is insignificant as a number. So what we've got is an extra row here of all of our missing data, which is now 0. We've got no missing data. The data set is cleaned. That's it. There's no more missing data. And we only lost 2 records where embarked was empty. That said, we had to make some approximations to fill the gaps in age and cabin columns, and those will certainly influence the performance of any model we train on this data. Yeah, if we were to go further, then what we would do is to find the value either side of the missing data and average those two and put that in the middle. Now, that's something we could try. What do you think, Ritu? Do you think we could try that? Who knows?
Sorry.
No, it's fine. I was just thinking that in what happens often in systems now is that they go one step further and they don't average the whole row, but they average the data points for age, for example, either side of the missing one. That's assuming that we reorder the ages. They have to be in order. You have to put them in age order in order to be able to make sense of the missing value. Anyway, there you go. And then you can find an age and a missing column, and you can then put that value in there. So let's quick look at the summary before we move on. So missing values can affect the way a machine learning model works. So it's important to fill those gaps in the data where they are located. You are now able to get the big picture of what's missing by using lists and charts, and also selecting only the specific items that need to be addressed. We practice finding and visualizing missing values, checking whether a data set uses value 0 to represent missing values. So the isNull function there. Well, that's for it's empty. We actually check specifically for zeros being used. Dealing with missing data in 3 ways: removing the rows, replacing the missing values with the mean or median of that particular feature, and creating a new unknown category if dealing with categorical data. So not numerical, but categorical, i.e. something like cabin or cabin number, which isn't really numerical. Let's examine different types of data. It's going to move on. I'm activating my sandbox. Have a quick read of that for 4 minutes. And all those things I've been saying to you about whether data was continuous, categorical, or ordinal. Ordinal is a that can take specific values, discrete values, that whereas continuous can be any value in between. So have a look at it. You can put something in an order, whatever that order is. As I suggested before, putting the ranges in order, there would then be an ordinal row. They don't have to be obviously numbers to be ordinal. I mean, you can organize things in terms of bad, better, good, very good, best. That's an ordinal. Anything that ascends or descends in some way can be seen to be ordinal. That's the point. Doesn't have to be numerical. In fact, those things that you see very often when you're asked to evaluate something, in terms of like in Amazon, where you press the number of stars, or anyone that wants a review about what's been done between poor and excellent, there's a special name for that. It's called a Likert scale. A Likert scale. So a Likert scale is an example of an ordinal. Okay, and we can move on. So continuous data are numbers that can be used by any amount, however small that is. So a continuous range. Category ones that don't fall on the spectrum, they can be usually they're mutually exclusive. I mean, you can be in two categories, but they're not in a range. Can't really say 1.1 times staff or 1.1 times passengers. Doesn't really make sense unless you're going to declare it as a new category called 1.1 times passengers. Doesn't make sense to multiply numbers and categories unless you're looking for the population of something. Then that might help. But in general, these are the three key data types that we will look at. And of course, identification is one as well. Now, if you remember back when we first looked at the first calculation we did on which delivered a data, which delivered a value, it told us that it was a D64. So it was a 64-point floating number. And that means the precision that was being used was 64 bits of information. So it was described in 64 binary bits. Now, we have much more general data types here. The common ones are obviously integers, so whole numbers, floating point numbers. So this is the most common ones that we use. Now, you wouldn't normally, if you're doing a loop of some kind and counting down and counting up, you wouldn't use a floating point. You would tend to use an integer for that. If you were counting how often you did something, you'd have it as an integer. However, if you were looking at something like the average number of times that you did something, then you might well end up with a float. And in fact, in some programming languages, you have to specifically tell it that you want the result as a float, because what will happen is if you divide two numbers that are integers and the result comes out at less than 0.5, the system will round it down to 0 because it's looking for the next integer. So you'll find, and I have found in the past, lots of problems because the system hasn't realized that I wanted the result as a floating point. So what you can do in other programming languages is before you what you do is you divide one of the quantities by a float 1.00 or something, and if you do that, it will then express the answer in that format, and so you will see values of 0.222223 instead of 0 for your average. So, but nice thing about Python is you don't need to do that. Python's smart enough to realize that if you divide 2 by 3, 2 by 7, the answer is 0.14, it will come up as 0.14 something or other. It won't say 0. It's because it won't round down. So that's the relationship. Larger numbers and small numbers obviously can be represented by the floating point numbers. Now strings, there are the letters, usually for letters or words, and always a string is in a double quote. Something is a string. If you assign a string, it's usually yes in double quotes, and there are many string manipulation functions. String length, string substitute, string index, where you're looking within that string for a particular item, and also it will return the value where that substring starts to appear in the main string. So if you're doing some kind of long string manipulation and you want to extract, for example, I'm going to have to write functions which can look at an examination question of, say, 1,000 words, up to 1,000 words at the most, and it has to find where two keywords are next to each other in that string. And so that will be a fairly complex arrangement of string index functions to find out where it is, or string search functions. And then when it finds that, it has to say whether they are left or right or left together. And if they're not, then carry on moving through the string. But usually search functions like search string ask you where to start to search. And so what you can do is combine your string index functions and your string search functions to go through a string very carefully, picking out all the things you need. So strings are very powerful. Different systems have different maximum sizes in terms of the size of the strings that you can have. But they're usually of the order of several megabytes of data for a string. Some languages have much shorter sizes of strings, because sometimes it can be, if you want to manipulate a CSV file, for example, it's much easier to read it into a string, and then you can then make it into tables and do what you need to do based on the comma separated values. So you can then just pull in chunks and blocks and make whatever data bits you want from that string. It's not really a good idea to keep reloading bits of your string back into a file on disk or wherever it's stored in the cloud. The reason for it is it's very hard to keep track of the status of something that's on the disk without keep reading it back and making loads of checks. Whereas if you keep it in a string all the time, then you can really manipulate it how you need to. So Booleans, these are all true and false. So, and an alias for true and false is 1 and 0. So, for example, these functions for string index of something, if the index isn't found, if the string isn't found, it will kind of return a false. And then that way you can then logically combine conditionals. So a conditional that returns a true or a false, you can then say, if this and this, then off you go, do something else. So you can combine conditionals because they always return a Boolean. They always return either true or false. Named after the Reverend G. Boole, who was the first person to really apply logic in this situation. Believe it or not, the first application of Boolean logic in a system was to control the gates in a milk dairy, to control the way that the milk would flow from one cowshed to another one. Not cowshed, but the place where the milk was processed. So using these combinations of Boolean logic, and they all combine together into interesting theorems of and or. Also, chips, microchips, they are all based on these, what they call gates, these Boolean gates or logic gates, which, depending on the value of their inputs, return a true or a false on their output, return a 0 or a 1. So, for example, an OR gate, like in an OR function here, would return a 1 if either one of its inputs, any one of its inputs, is a value 1. So it looks at all of the inputs and said, if the first one, or the second one, or the third one, or the fourth one as an input is a value 1, then the output is 1. And it's the same thing here when you do a logical OR in Python or anywhere else. And is the same. It means they all have to be present in order for the output to be 1. And there's interesting other functions. You've got something called an exclusive OR, which means it's only looking for a 0 or 1 or a 1 or a 0 on the input for the output to be 1. So what it's saying is exclusive OR means it wants to see a difference between the input and the two inputs and to get a 1. They're the key functions. All of the others that there are can be simply derived from those. And in fact, you can derive the exclusive OR from a combination of ands and ors and not. And not is simply negating it. So if you put a 1 in, you get a 0 out. If you put a 0 in, you get a 1 out. And so that's how you can combine logic gates to do things. So that's Booleans true and false, and none, void, null data, or rather than the absence of it. Okay, so they're the data types. A null is a very powerful thing because the nice thing about a null or a void statement, do nothing, it's very powerful because it does not change what the program does. So, for example, you could say do nothing or operate on this void and then do your program, or you can say do your program and then operate on this void, and it has no effect. And that in itself is quite a powerful idea, that that operating on null data doesn't actually do anything. But it can be very indicative, as we've seen when there is null data, of is that data set representative? Is that data set complete? So it's a very powerful idea in terms of understanding data, the missing data idea. So the exact terms and implementation for these concepts varies from language to language, that's true, but the basic way they work is much the same. It's notable that some circumstances, two different data types offer equivalent functionality. True, false values can be encoded as Booleans, or yeses or nos, or noughts or ones, or even floating point numbers, 0.0 to 1.0. So depending on what your system is, it will return those values. And there used to be something called casting, where it would automatically work out what it needed to do, and it used to often get it wrong. But since the days of Python, which is about the last 20 years, it's been pretty good. Most languages now don't make those kind of mistakes and don't insist that you use exactly the right kind of data type. The reason why we had those in the past is because memory used to be expensive. And if you were storing large amounts of integers, you did not want it to store it in, as it was then, 32 point, which are 4 bytes of information per value, when you could do it in 8 bytes. You know, suddenly, what was an expensive thing, you were using a quarter of what it was before. So the idea is important. Also, the time, the processing time of an integer is going to be less than the processing time of a float. I mean, if you were talking about subtracting 2 from 3, that would be done faster than subtracting 2.000000000 from 3.00000, because the algorithm would have to work through all of those zeros to make sure that they were in fact 0 and didn't have a number in them. So it would run faster. So now those are not considerations anymore. Nobody cares about speed. The only people that care about speed now are weathermen, because they have the fastest computers in the world and they're still not fast enough. So you have to, and they can now only really model up to 2 weeks in advance with any kind of accuracy. That in itself is massive, because up until recently it was only a few days, and even more recently before that, you know, down to maybe 1.5 days really accurately. And say they use the fastest computers in the world, and they use the best high-speed programmers in the world. So they're the only people that really care about performance time. Having said that, when we're working in the cloud, as we are, that can take time to upload and download. Also, if you've got a lot of calculations to do, I mean, when I first started off on my project, my first data set took 3 weeks to process. And I was watching it every day as it made progress. I've now optimized it and it runs a lot much faster than that. But even so, for example, to get Excel, if you write a Visual Basic macro or something in Excel to update the value of 1,000 by a 1,000 array, which I've got for my keywords, just simply update the values. So that's 1 million cells it has to update. It takes 18 hours. Yeah, 18 hours for Excel to do that. Now, the point about Microsoft is that once you really get into this, it's possible to rent time or get time in the cloud and get processing time. You can get much faster machines up there and be able to upload your data, let them process it, and then you download it yet. I haven't got to that stage yet. I'm still happy to chug along. But my latest project means that this has to be done many times, because I'm looking for an optimum value of something, and I need to be able to do that many times. So let's move on. So knowing what kind of data you have helps you pick the right data type. The correct data type can depend on the package you're going to run in your models, though generally the packages are quite permissive. Generally, if you're working with continuous data, use floating point. Ordinal data is typically encoded as integers, like in loops and things like this. Categorical data for only 2 categories can usually be encoded as a Boolean. So you can say is something or is something not that thing. Working with 3 or 4 multi-characters can be slightly more complicated. This is something we'll cover in the next lesson. Okay, yeah, we can define a set. In the next exercise, we'll practice visualizing our data in order to understand it well. When we do, we take special note of the data types that are being processed and try to identify which of these is continuous, ordinal, or categorical. Yeah, okay. So we'll dash off. We'll come back at 10:52. Sorry, 10:52, 10:42, and we will work to try and predict our missing values. Okay, back in 20 minutes. Sorry, us roomies were chatting. Anyway, let's move on. I'll give you a minute or so to gather yourself, and then we'll carry on. So we're going to start working with data to predict our missing values, not just delete the column or set them all to 0 or even set them all to the average of all of the others, but to predict what it might be based on everything that's around it. And that's based on its local information. One thing on floating points, when we talked about the power of computers, they tend to be gauged on the number of floating point operations per second that they can do. So if we just Google fastest computer, and we do it in terms of flops, which are floating point operations, China's was ranked the world's fastest 338.86 petaflops. Okay, so here we go. A megaflop is 1 million point operations per second. A gigaflop is 1 billion operations per second. A tetraflop is 1,000 billion. And then after that we have, I think, what's peta is 18 anyway, 10 to the 18 I think is peta. So that's 10 to the 18 floating point operations per second. That is very, very fast. Supercomputers, let's have a look at this on Wikipedia. Supercomputer, 100 petaflops. There we go. So it's now done in petaflops. So let's see how many numbers, let's confirm that. What a peta is. Peta as a unit. Peta is a decimal unit, 10 to the 15, not 10 to the 18. So there they go. There's all of the going there. So we've got mega, giga, tera, obviously as in terabyte for your hard disk that you might have. And after that, it becomes peta, 10 to the 15 million, 10 to the 15 operations per second. That is fast. Okay, good to know. Right, shut that down and move on. Oh, didn't mean that. I meant that. So we're working with data to predict missing values. Let's continue. So our sandbox is there. I've got 21 minutes. Oh dear. So to build better machine learning models, we have to understand the data we're working with. This usually means both visualizing the data and understanding the kind of data we're working with. It's exactly true. My Dr. Rice, my supervisor, is setting me on several tasks to try and visualize the data that I'm working with using various techniques to have some understanding of how the different items are related to each other, and that's often easier to be seen by visualizing it in some way, and also understanding the kind of data we're working with. Yeah, we did a transformation on the data, and it came up with some very interesting results. So, and we're pursuing those, or I'm pursuing those. In this model, we'll practice cleaning our Titanic dataset and visualizing different kinds of data, particularly those that are continuous, ordinal, categorical, or simply identity columns. Again, we're using that lovely little Python script that they provide for doing some graphing. and and of course graphs is actually pulling in a very powerful graphing library called Plotly, and I recommend you get into that. I've got a course on it somewhere, video course on Plotly. I might be able to find some way of getting that to you if you're interested in going further with graphing. We
yes.
use this. Sorry.
Yes, please. If you can give us some link for the Plotly.
Yeah, I'll try and do that. It's not on this laptop, but I shall get that. Okay, we use this script to help you focus on learning data exploration rather than getting bogged down in understanding Plotly. If you like to look at the code for this custom script, you can find it in the GitHub. Okay, let's move on then. So starting as before, we're going to load up pandas. We're going to get all our files. We're going to read the data set in, and as usual, let's see where we are in terms of the first 5 rows. There's our first 5 rows, and as you can see, that's now back to where we started. Okay, we've reloaded in the data set. All those changes we made of filling in the zeros and filling the numbers with zeros and filling in the ages with the overall average age, that's all gone. This is the original data set again. We'll take a look at the columns and we can identify which columns hold continuous, ordinal, categorical, or identity data. Okay, so let's have a go for these 5. The passenger ID, what do we think? Do we think integer? Do we think continuous? Sorry, do we think continuous, ordinal, or categorical?
Identity, maybe?
Yeah, I think it's identity, isn't it? Yeah, because the passenger ID doesn't really have any properties in terms of being put in order. Like if they were numbers, for example, if they were number of bags brought on by a different passenger, then you could put those in an ordinal value, couldn't you? In an ordinal set, in number of baggages, you could do that. It wouldn't be continuous because you're unlikely to have 1.1 bags. So you would certainly have it as ordinal in that situation. So we can display a brief summary of the data types using Pando's info method. So Pando will tell us all about our data set just by typing info. And it's now saying to us what the data type is. There is non-null count. So this is saying, before we looked at the null count, but this actually gives us the non-null count, which is helpful. We can see here there's quite a few null ages that have not been filled in, and a very large number of null cabins that have not been filled in. And so the passenger ID is given as an int64 in each case, and the name is given as an object. So that would really mean a kind of category. That's a categorical data. Ticket is an object, so it's category. Fare is a float 64, so it's continuous. You can have any value of fare, really, as far as we're concerned. And so that will give you some idea. We've got 5 int64s. So this is a number. These are numbers. So these are integers. It just means 64 means that you can use 64 bits to represent the integer. So it can represent very large integers if need be. So we've got 2 floats 5 id64s and 5 objects in the first 11 parts of that. And it even says you how much memory is being used. So there you go to do it. Okay, so let's move on. We can see that several columns are stored as numerical data, those with int64 or float64, while others contain more complex data types, those with object as their D type, which is an interesting idea. So it's given data type object. So visualizing the ordinal data, let's start by visualizing some ordinal data we have available. The passenger class, so that's the ticket class, the number of parents or children on the ship, the arch, the number of siblings or spouses on the ship, SIB-SP. Okay. So these are ordinal data, so they're usually, in this case, ones that we can put in an order. We can say someone has ticket class 1, 2, or 3, and the number of parents. Again, we can order these values. Ordinal data can be viewed on almost any kind of graph. Let's start with a simple histogram describing relationships between the ticket class and the likelihood of survival. So we're doing a histogram of the data set, and the first label on the x-axis will be P class and y-axis survived, and the function we're going to do is the I can't read it. It's gone on too far. Yeah, it's the average, but let's including box plot is true, including. So what we're going to get here is a histogram with box plots. Basically, that's what we're going to see, which looks a bit like this. There we go. There's our box plot. It enables us to see where the population is. And there's the average number of survived and the P class. Okay. Let's have a look at this if we can get back exactly where we were. Data set survived. So this is the function that we're going to ask for. We're going to ask for the average related back to survived, box plot true, which is this thing here. Okay, let's move on. The box and the whisker plot shows that at least half the people had third class tickets. Note from the median and maximum of the plot, both sit at P class equals 3. Let's have a look at that. Yeah. The median sits at 3. And the maximum for also sits, doesn't go any further than 3. Yeah, obviously that's obvious because there isn't a 3.5 class. Okay, the histogram shows us that people in second and third class tended not to survive the wreck. That seems about right, doesn't it? Everyone on average, people in first class survived. And that then becomes the point that you were saying, that this is looking in average how many survived. And when we looked at the absolutes, we saw that there was a much bigger difference. And it's only when we average it that we get, we then effectively have balanced the data set more when we look at the averages. Okay, the box, yeah, we've done that. The histogram shows that people, yeah. Let's look at how survival varies depending on whether you had parents or children on the ship. So it's similar as before. It's done by multiple histograms of the label for the x-axis of the passenger class, and the group is whether or not they were parents or they had children. And on the y-axis, as before, we're talking about survived, and the function that we're applying is average. This is quite a clear way of laying out any call, really. If you do that, then you won't go wrong. So end each line with a comma and then a hash for a comment. This is good practice. It makes readable code rather than trying to put the whole thing in one line. You can actually then interpret each thing step by step as it goes through. So I would recommend that you lay out your function calls this way. And here we go. So we've got by class, group the tickets by class, what the number of Parch, what was that? Parch was the parents, wasn't it? Whether they were parents, whether they had parents or children. Yeah. Okay.
So basically, family.
Yeah. Yeah. Whether they had parents. Yeah, that's right. Yeah. That's quite an interesting one. I like the colours. Nice, simple. Because I think what graphing has done is they've taken Plotly, which is not really for the casual user, let's say, and they've given us a nice, simple interface. They've actually written a kind of an API to go into Plotly, which they've called graphing. It's quite a nice idea. And if we look in graphing, we'll see probably a simple translation between this and the actual Plotly commands. But rather than explain to us in detail precisely how Plotly works and how it should be used, they provided this nice friendly front end. So the first and second class ticket holders, people in larger family groups, appear to have better rates of survival. These doesn't seem to be the case for the third class passengers, though. Doesn't seem to make any difference at all what your value of parentage was in terms of number of children. And that tells you something, doesn't it? That tells you, yes, tells you that they all got wiped out, really. So let's see if those with different ticket types tended to be different in different sized families. A box and a whisker is a nice alternative to a histogram when we want to look at a spread of data. So calling graphing with box and whisker on our data set, nice and straightforward between two labels. So we're not doing anything else. There we go. So we can look at the spread of data for the first class, second class, and the third class. And as we can see, yeah, goes right the way up. Well, SIB-SP, what it's saying is that regardless of the number of siblings that there are, it didn't seem to matter. You got a whole spread. And with these first and second class, it's saying to us that there isn't really much of a spread. It wasn't Yeah, more siblings, yeah, in general. Yeah, you've got more siblings in third class. The box plot, well, it gives us the median and the upper and lower ranges. So it gives us our spread. Most values are 0. This tells us that most people were traveling without siblings and without a partner. There are no obvious differences in the values between the ticket classes. So that's here. No real difference here, which is interesting. And it could be that because most values are zeros, that in itself means that what we're looking at isn't representative in some respect. So visualizing continuous data. Continuous data is usually best viewed either using an XY scattered plot. So it makes no sense if you've got categorical data to do a scatter plot, because they don't really have values that are relative to each other. Their only value really is their number of them and what they are. So they're not continuous. So a scatter plot doesn't make sense. But we're asking the question here. If there isn't an obvious relationship, we're going to see if there's a relationship between two continuous features. So what it's asking there is histogram or box plot to look at the spread of data. So our data set age and fare is continuous, and let's view them. So for example, we could go back to all the work we've done before and try and predict the age from the fare or the fare from the age using a regression. This is what we've done before. We've got data, we've got samples. We could investigate if there was a regression between the two. Be interesting. Yeah. Oh no, between the age. Yeah, that's right. Is that true? Is there a relationship? Can you predict someone's age by the price of their ticket, or vice versa? That's what we're looking at. Yeah, more expensive ticket. Yeah, but I think that's going to relate to the class. But let's see. So here's our scatter plot, 2D scatter plot, and it's showing for all the possible ages how much they paid. That's interesting. Seems to me there are different age groups here. There's this age group here. So obviously the children tended to be in the lower classes, so they paid a lower fare. And then as soon as you got to being an adult, then they started to pay an adult fare, of course, at that point, as soon as they were 18. And it decreased around 50. Yeah, and beyond that, there were some peaks. And here was 64, an interesting one. So that could be people that that were retiring and going to America for a holiday. That sort of peak could have arisen there. Yeah, my guess is they could have had rich parents that wanted them to have their own room. Yeah, so they had their own room, maybe the room adjoined with the door, so that the parents could. Yeah, that's right. Yeah, that's true. Yeah, but these ones down here, that could have been, I say, because for adults having an adjoining room with their young children, if they could afford it. So that's maybe why those two children appeared to be paying a lot of money for their room. Also, it's possible they might have been unaccompanied. They might have been sent off by one parent to visit another parent in America, And yeah, so social services should be involved here. We should involve. Well, the data's there. The data doesn't lie. Actually, the data does lie all the time. So, okay, so there is an obvious relationship between age and fare. I think that's reasonable to say that. So does the cost of the fare or the person's age have any relationship with the likelihood of survival? So we're going to use our graphing. We're going to do a histogram. Our key point is it survived. The original data set, uncleaned. Yeah, uncleaned. Yeah, and let's have a look at this. I won't keep explaining what's happening here. Let's just look at it. Oh, my sandbox ran out. Oh dear. I hope I don't have to start again, hopefully. Let's go. Let's say I need to start again. I just know it. Oh, hang on. Maybe there was no, there wasn't one. We didn't miss one. Oh, I think that's what it is. Graphing is not defined. So let's see if we can get away with going back to when we import graphing from the top. In pandas, when do we import graphing? We import graphing, it's before that, isn't it? So we have to go back to where we okay, data types.
You try Control F and then you can perhaps search.
No, hang on. Yeah, well, really, what import graphing? Yeah, you have to find the statement import. We have to go back as far as graphing.
This is it.
Import graphing. Here we go. So this was the first error that I got, that it didn't understand graphing. Then it's going to say it doesn't understand pandas. But let's see. No, okay. So we have to go. Oh, you try that. So how far did you go back then to pandas? So we have to go back to pandas here. Yeah. That's the whole point about this. Obviously, because it's accumulative. So I'm suggesting that everybody goes back to this point here, where it says preparing the data, and run it then. So we have to run that one in your new sandbox. And when that's done, just make sure that ran okay. Yes, it did. So immediately go on to the next one. No, we don't have to worry about shape. Yeah, that's right. So missing data, calculate missing data equals data set, rename. No, we can go on. We need that one. We need missing numbers. No, one before. Oh, I didn't see a pandas on the. But was. Okay. In that case, let's move forward. If there was another pandas, let's find it. Work with data to predict. This one here. Okay, so this is our one here. We're going to do that one. And we don't care about that. We don't care about that. We need to import graphing, yeah. I'll check if everyone's in the right place in a minute. So we've got graphing, no. No. Graphing histogram, visualizing. Oh, so we're here, aren't we? So we're now at the scatter plot here. Whisker box between data set and fair. That's what we just looked at. So let's run that again. And we should be there. So can you, Rita, are you there?
Yeah.
Good. And we're all here, yeah, at that point. Let's move on then. There should be a way of automatically doing that. So fair versus survival. That's interesting. Fair is here. So this gives us the number of people for the fair. And survival is your average survival. And it seems like yeah, it didn't. Interesting. Fair is 250. People paid a lot of money. Yeah, only one person paid that money and they survived. 2, yeah. Yeah. It's not quite. Not. Yeah, there's something here that's interesting. This step here definitely indicates a relationship between the fair paid and the average survival, doesn't it? Yeah, these were the people probably not in absolutely first class, but in the other classes as it went down. And that obviously was reflected. Yeah, could easily be. Yeah. Also, interestingly, a few people, it'd be interesting to investigate the age of the people that paid a high fare and didn't survive, because I would suggest that they were going to be older people that decided that they were just prepared to go, prepared to die rather than panic and fight through all of the other people. They would just, they just accepted that it was going to happen to them. And that might be just older people that paid money that yeah, that's me. They probably paid a lot of money to get onto the boat. They probably paid, serious cash to someone to get them on that boat. Because it was a women and children first thing. See, that's the other thing they should have indicated, because yeah, it does show that, doesn't it? Yeah, kids survived. Younger, I mean, because it was women and children first. So the young children, especially, if you were like 18 or something, then you weren't going to go by as a child. But kids of the ages between 5 and 10 had a good chance of survival because they were plucked by their parents and put onto the boats directly. Yeah. Yeah, I think the interesting point there is that they're ones that couldn't be carried. They had to make their own way through, and with panic and all the people rushing around and doing crazy stuff, those kids might have easily got lost. you lose track of them. Whereas the ones up to the age of 7, you could hold on to, and that might be a factor. But there was a policy of women and children first, so it would be. I would be interested if we had the data on women and children to see what chances that was, regardless of age, women and children. But we can't do that because it didn't give us the sex of the people, did it? That's not a field that's available to us. Oh, it is. Oh, we've got male, female. Oh, that would be interesting to look at. That would be very. Oh, here it is. Look. Okay. We have the following. Yeah, we've got male and female, but yeah, we've got that. Okay. In a similar way to ordinal data, but with the data viewed as an orderless groups. Alternatively, categories appear as colors or groups in other kinds of plots. So this is a bit more complicated. Let's look at it. It's now taking in a plotly function. So instead of using graphing, which in itself calls plotly functions, this is calling a plotly function directly. So we need to create these user-defined functions, these local ones, and it returns the rows that match in terms of sex and embarkment port. I don't get quite the relevance of that one. And the proportion survived, and that's the end of that. So we've got 2 user-defined functions there, and we've got our 2 columns of data. Together, these represent each combination of sex and embarkment port. Okay, so we've defined these lists here to be the different columns, and let's see how it is.
It could be
calculate
that
number of passengers at each port, so passenger count. Yeah, they're using length of the get rows of the qualifying character for the table that we've got, and then we're calculating the proportion of the passengers from each port using this function here, and combine them into a single data frame. Okay, so what we're doing now is constructing a new data frame here, a new dictionary, in fact, where these are the keys for the dictionary. And then doing something called a bubble plot, which is really a 2D scatter. Okay. A dictionary in Python is a way of setting up a set of keys and values. And that value can be either just a single point. So, for example, you could have car Ford, something like that. Or, as we did earlier on, when we set up 2 fields, each of the fields was a list of numbers, and then you can have really the actual data types you can have in the dictionary, in the value part of the dictionary, is unlimited. It can be another dictionary, for example. So you get nested levels, or it can be a list, or it can be a single item. But it's a really nice way, and there's a lot of really nice Panda functions for reading the dictionaries back into a table, for example. Yeah, you could just put them in a dictionary with a key value. So you put in the key and you get back the value. Yeah, that's how they work. So let's move on. Let's just have a look at it, shall we? Oh, look at that. Bubble plots. Oops, missed it. Nope. down here, down here, down here, down here, down here, down here. Here we go. A bubble plot of categories. So port against the sex here. So this is like a clustering, really, in its own respect. Southampton. Hang on, I'll get this right. Port equals C. What was Q? Yeah, it's the 3 ports that people have got on. I think it was Cadiz or somewhere like that in Spain. It went to first. Something like that. Let's Google it and find out. Titanic ports. Ah, there you go. So it was Cherbourg, France. And what was the Ireland? Ah, okay, it was Ireland. Yeah. So there you go. So that's what it was, Southampton's. Yeah, they're the 3 places. We can also see that people boarded at Southampton. It does seem there is a weak relationship between the port of boarding and survival. And that kind of makes sense because, sorry? Yeah, but the point is that it would have been ticketed. You wouldn't get on without a ticket. So therefore, it kind of didn't matter where you boarded because you would be allocated. Unless, of course, you were in the lowest possible class. But even then, you had to have a ticket to get on, even if you were in the lowest class. So in that situation, it wouldn't. Yeah, maybe because they went into the less deep down in the base of the ship type places on a first come, first served basis. So what you would have had is a ticket, not to a room. So in the lower classes, you would have been able to just be sleeping on. Yeah. Yeah. No, you'd like these in steerage. Yeah, in steerage, you'd have. That's right. Yeah, back then you'd have like a room like this with just benches and beds everywhere. So there would be no, yeah, just like a party, really. You know, there's no allocated sleeping places in third class and in steerage. So there we go. Yeah, you can make that in a sense when at the end it was a real panic and people didn't really care about anybody else. They just wanted to survive. You can be absolutely certain that men would have dragged the woman off a lifeboat, chuck her out and jumped in himself. You know, that would have happened. Also, yep. It would happen. Of course, it would. It's survival, isn't it? I mean, the men are generally probably stronger than the women. So in that situation, they would probably have survived. Also, yeah, it could be. Yeah, maybe. Yeah. So it really made a difference to pick your spot. That's the conclusion there, isn't it? That it made a lot of difference which place you were going to be in. Looks like women have a much higher survival rate than men, but there were more men on the ship. Well, I think the women had a higher survival rate because it was women and children first. They were more likely to be on the lifeboats. The lifeboats. That's the point. So there could have been, there's two factors at play there at least, probably many more. Yeah. Yes. Oh, the magnifying glass. I'm doing other things here. Yeah. Zoom in. Let's come back. That's it. Okay, so now I can see. Yeah, that's interesting. Interesting these to investigate the data. Ah, that's where we started, I think, isn't it? Okay, that's good. So you can be sure that this little project that we do after Christmas will involve all of these things in looking at the data. So we can see that most people boarded at Southampton. Doesn't seem to be in a weak relationship between the port of boarding and survival yet. So we learned about different types of data and practice exploring data through graphs. Through these, we discovered that some features are related to others and that survival seems to be influenced by many features. Okay. One hot vectors, that's an interesting subject. That's a, yeah, yeah. What do you need to be to guarantee the highest probability of survival? That would be interesting. It probably says you have to be a man and a woman. Because it's a man from some perspectives and a woman from others. It depends what the dominating factor is. But that's yeah. Well, I think we'll include that idea in terms of the if we do this project concerning the job market. That's one of the things that we can look for. What is the ideal candidate? That's it. That we'll put that in as a little exercise to find who's the ideal candidate. What do you have to be? And then just try and be that whenever you go for a job. Well, we should include, if I can get some data on how useful being on LinkedIn, for example, is, your profile, how important that is as well. We can include that as a field, as well as the stuff that we can extract from the data site itself, because that's an interesting, if we can get that data, that would be very good. Also, we should be able to get information on whether the people have attended any job skills training. That's another thing that we can use to analyze and see what kind of training it was, where it was, and what was the most effective, and so on. If we can get that kind of data, then I'm sure we could do some really good analysis with that. So let's go to one hot vectors if we're all happy with where we are. I think with practice, you can go back with all of these functions, graphing functions, investigate what they're really useful for in terms of a data set, get effectively a use case almost for each of the graphing functions, and take it from there. So let's move on with one hot vectors. Okay, have a read of that. It's an interesting topic. Okay, hopefully we've read that. And it confirmed what we said before, that deleting the row is not a particularly good idea. And statistical power is reduced very often if you eliminate a row. It makes no sense to try and deal with what is in fact categorical data as if it's continuous. It just produces nonsense trend lines. The method that can work, provided the number of classes isn't very large, is one-hot encoding, where you can take each mutually exclusive event, because something is either, in this case, Cherbourg, Queenstown, or Southampton, and simply code that as an event. And once you do that, you can then look into those as extra columns, and that gives you more information, numerical information that you can use. The problem with one-hot encoding is if there is a very large number of classes, a very large number of fixed options or fixed values for something to existing, in which case it can get incredibly noisy, and something that looks important actually isn't. So we have to be a little bit careful about how many extra columns we introduce that contain value, data of little value. One-hot encoding doesn't work very well if the thing you're trying to encode is allowed to have more than one value. So, for example, if you were talking about an England port, it might have been Liverpool or Southampton. So these have got to be, in a simple one-hot encoding, they have to be mutually exclusive. The classes are what are called monomodal. They're in one category. Our events. So again, statistical power, we mentioned that for the first time, and we kind of alluded to it when I said it wasn't very good, or it's not very good for the model. It all comes down to how powerful conclusions that you can make by applying. If you've got lots of noise everywhere, you only really want to include those features that are statistically important. For example, if you're analysing tweets, and a lot of people do, then the use of slang, or what they call colloquial language, is a definite indication of sentiment. But in my situation, where I was analysing exam questions, it's very unlikely there's going to be any slang. So to put a column in to deal with slang would simply be unnecessary. So it's what's appropriate in terms of what columns you include and what are significant. And that's what all this is about. This is about reducing the number of our columns to ones that have significance, because that will increase our statistical power. And one-hot encoding does that, because it takes something we've not used so far, which is which port we boarded by, and we've now encoded that. And this thing here, if you put in worthless columns, you will get lower statistical power. And of course, as we said before, one-hot encoding can reduce it if it means that you're adding lots more columns. So let's have a quick look at our next exercise. So we're going to predict unknown values. In this unit, we'll build a model to predict who survived the Titanic disaster. While doing so, we'll practice transforming data between numerical and categorical types, including one-hot vectors. Now remember, a vector is simply a comma-separated, usually, data point. And each of those items between the columns are aspects or features of that vector. In a simplest form, if you've got the values x and y, then your vector could simply be xy. That's your vector. If it's 3 dimensions, it would be xyz. If it's this the port of departure vector will be the 3 values are the ones that we've looked at here. Okay, so and the vector then simply takes the value for those features 0 or 1. So we'll open our sandbox, clean up the data set as we did last time. Remove the missing age values just to get back to where we were before. And there are our rows. And we've got just what we had before. And we've got an embarked thing here. Now, at the moment, in this format, we can't do anything with these. But if we can convert embarked into a one-hot encoded vector, then we might be able to do something with it. So let's do it. We'll be training on a type of model called a logistic regression, which will predict who survives the Titanic disaster. So whereas a normal regression will predict a value, a logistic regression will predict an outcome. Okay, whereas before we were talking about the number of bike rentals or the price of a house, that was a regression to predict a value. But a logistic regression applies a logic to the output of your regression to say whether or not a condition is met and whether the output therefore is true or false, and therefore who did survive and who didn't. So it's applying logic to a regression. And you can read a bit about it. So let's create a model using only the numerical features. We're going to use P class as our ordinal feature because it goes in as 1, 2, 3 rather than hot coded categorical values. And let's move on with it. So we've got numerically only the log loss cost is 0.6. So what we're doing is from the logistic regression, import train logistic regression. So that's the function we're going to be using. Be nice if we used it as something else. So the features that we're looking for are age, the passenger class, siblings, parentage, and fare. And we want to consider, so these are the ones we're considering to use. Yeah. So what we're doing is these are our columns. So a bit like the bicycle rental and a bit like the house prices. These are the features that we're going to look across. And we're going to train our data set, which is our table that we've got, on those features. Okay. And we're going to print the final loss figure. The idea of a log lost is just to be able to contain the range. So that is when it's trained, that's what our final numerical only loss was. Did that. Let's then binary. Let's see if we can improve the model using categorical features. So categorical features that have two values that can be encoded as a single column, 0 and 1. So this is where the logistic regression comes in. It's applying logic. Let's convert sex values into is female and put 0 and 1. So as many as we can, we're going to try and convert our columns so that we can model them logistically as being is something, is not something, rather than at the moment it's categorical between male and female. There's nothing in our model that says you're either male or female. All at the moment we just say it's male and female are examples, but by categorizing them as either 0 or 1, then we make a statement, we make a constriction or a constraint on what that is. So let's see what effect that has, and let's see what effect it has on the loss. Should improve it, hopefully. So yeah, the loss has gone. The final loss has gone down to 0.47 because we're now giving it more information to be able to use. We're telling it that on the sex it's either male or female, and that should be seen as a 0 or 1, and it can use that in working out the logistic regression. And let's keep going. So our loss has decreased. That means our model performs better than previously. And let's see what one hot encoding does for us. So the ticket class is an ordinal feature. That means it has 1, 2, and 3, and it's treated as having an order and equally spaced. It's possible that this spacing is simply not correct. So in stories that we've heard about the Titanic, third-class passengers were treated much worse than those first and second class. So we're going to assume that that works. So we're going to invert the class into a categorical feature using one hot encoding, meaning passengers have only got one class in this case. They're either in class 1, class 2, or class 3. Now, as I say, up until now, that's not been explicitly encoded into our model. All we got up until now is that they're either in first class, second class, third class. They could be in fourth or fifth. It might exist, but we don't know. By doing one hot encoding, you're saying they're the classes that exist. That's what you should be using. Okay, so it turns it from an object into something that can be handled and manipulated, and you can extract further information from them. So let's see. What's happening here is that we've got our possible values for the so dot unique gives us the possible values that have currently occurred that we've got, not so that should come out as 1, 2, and 3. They're the unique values. And then we use pandas one hot encoding to categorize it. So data set with one hot encoding is pandas get dummies, data set columns is P class, and drop the first is the false. So we keep all the values. Add back it into the old P class column, that's what that does, and then print out the first lines, and we'll see what we've done. So what we've done is we've now got a one hot encoding occurring across P class 1, P class 2, and P class 3. By one hot encoding, it means that only one of those are encoded. Yeah, and that's much more useful than just have an object 1, an object 2, and an object 3. We've now got a relationship, an exclusive relationship here, which when we put that into our model should reduce the values even further. So it's been converted into 3 values, P class 1, 2, and 3. And so let's now run it again and see the improvement that one hot encoding has done in terms of our loss function. And we'll see our loss cost function is now 0.47. What was it before? Slightly more than that, wasn't it? So we're saying it doesn't have an effect. So, as we've said before, one hot encoding can make your model worse. Yeah. Because it's including extra information that might have been ignored before, and now it's not ignored. So what we've done is we've told the model, this is important, don't ignore it, but it might not be that important. So that's the issue there. It's not the problem that the number of extra columns we've created is large compared to the number of samples we've got. That's not the problem, which can sometimes be the case. If you've got more columns than samples, you're in trouble, generally, when it comes to data science. Let's take it from there. So let's include the cabin. We've made things slightly worse, as it says there. So the cabin information is a categorical feature. It should be a good predictor of survival because people in lower cabins probably had little or time to escape. So we're going to use the cabin information actually as a categorical feature. Let's encode the cabin using one hot vectors and include it in a model. There are so many cabins this time, we won't print them all out. So we'll just move on. So we're doing a one hot encoding of all the cabins over those features, and we've got 135 cabins found, and the overall is 0.46. So that's our best so far. So by encoding the cabin number, sorry? Yeah, we want to get the lowest loss. Yeah, that's the idea. Because the loss is the error between the predicted value and the actual value. So what you predict as against the ground truth, that's your loss function. Okay. Uh, 135 different cabins. Yeah. So some people were in the same cabin. Obviously, I think probably in that situation. Yeah, we were. Yeah. So maybe that's why the improvement wasn't as much as we hoped. So let's see what else we can do to improve power. Yeah, exactly. Yeah. Yeah, more cabins. Yeah, it's very, very difficult, isn't it? I think it says here, including very large numbers of categorical classes, such as 135 cabins, is not the best way to train a model. This is because the model only has a few examples of each category in the class to learn from. That's true. So in that situation, you've got, as we said before, it's never a good idea to have more columns than you've got data samples. Yeah. Yeah. Yeah, but maybe, yeah, but then that's not really a one hot encoding. It's actually the individuals that it would be done. So, okay, so I think we will probably stop there and look tomorrow. Oh, we do improve comparing the models, don't we? Oh no, okay, let's go to the end then. So that's our best result so far. and I said they're using models can sometimes be improved by simplifying features. Cabin was probably useful because it indicated which floor. So those on the lower deck would have quarters that flooded first. So using deck information may be more simple than characteristics. That's what we said, using which level they were actually on. Let's simplify what we have run, replacing the 135s with a simpler deck category, which only has 9 values. Now, how do we get the deck? That's the thing. We've got all these decks here, these features, but we have to categorize how you get into that deck. Simplifying cabin into deck, 0.45. So again, we've gone a slight improvement there. My guess is that deck is a function that will take the how do we define deck? Deck, the deck that was on. So that must have been another column that we didn't see. Because we need to be able to derive what deck is. Because deck could be, the first one could be, it might be the first digit. So deck 1 and then up to 99 cabins. Deck 2 up to 99 cabins. Yeah. No, I think class deck A is going to be cabins probably from 0 to 100 or 0 to 1,000. No, 0 to 100. Deck B would be 100 to 200. Deck C, sorry? Ah, okay, so that's great. So in that case, we could just extract the deck. Ah, yes. Yeah. I think it's here, isn't it? Deck of cabin column names is the list of C for C in data set with one hot encoded column if C starts with deck. Yeah. One of those categories and does a one hot encoding on the deck. Okay, so that's what that does. Let's move it on. Let's try and run it. And we run that. We now compare our results. So again, we're gathering together all of the stuff we created here. And then we're sticking it into a data frame that we can then just display. And there it is, numeric features only, adding sexes to binary, treating P classes categorical. So it's getting better and better as we go down. The problem is we don't know what the final answer should be, what the best you can get with that data. Yeah, so we can see categorical features can both improve and harm how well a model works. Often, experimentation is the best way to find the best model, always, I think. In this unit, you learned how to use one-hot encoding to address categorical data, explored how sometimes thinking critically about the problem you're trying can improve a solution better than simply including all the possible features. So carefully filtering. So let's quickly do the knowledge check. Here we go. 3 minutes. 4 questions. How do we clean data before training?
Second?
Well, we know it's not the first one. Removing data by definition makes it less powerful because we don't know what happens when we remove it. So it's not that. Cleaning data helps us to select features that will be helpful for the model's performance.
Maybe third one, is it?
Sorry, Ritu.
What
do we think? Do we think the last one or the second one? Removing rows that have errors prevents these from misleading the training process. That kind of makes sense to me.
Yeah, same here.
Yeah. So let's go with number 3.
Because features, it's based on, like, it will depend on the data scientist and the business domain what features to select. So
yeah.
I think cleaning has nothing to do with that.
No, cleaning has got nothing to do with feature selection.
Yeah.
Feature selection occurs where you can do it actually before or afterwards. Like in my particular instance, where I'm looking for pairs of words. If I do the cleaning first, I might, and one of that cleaning is removing stop words, that might actually prevent me from finding one of my features. So in general, yeah. So what kind of data are best encoded with one-hot vectors? Well, I think we know this. With 2 possible values, yeah. It's a binary thing, isn't it? That's categorical data with 2 possible values. And the value is whether it's there or not. What is a data sample? What is a population? A sample is all possible data we care about. Population is a subset of that data which we actually have on hand. Okay, I think it's the other way around. Both population and sample mean data we can train our model with. A population is all possible data we care about. A sample is a subset of that data which we have on hand. I think it's that one, isn't it?
Yes. Right.
So with that, you have a model that isn't performing well. Which of these will definitely not help improve its performance? Adding additional samples, no, that will usually help. Adding a small number of features that you know are related to what the model is trying to predict. Adding a large number of features that you know aren't related to what the model is trying to predict.
I think first one might go if you have unbalanced data. First one only applies if you have unbalanced data and you are trying to balance it.
I see what you're saying, but we want to get as many samples as possible. That's definitely, but we're looking for what not what will.
Yeah, true. So last is not. Yeah, I could have got it wrong. Yeah, because not I missed. Yeah.
Oh yeah, as a binary. So if it's 2 or more, you need. Yeah, no, I think what they're saying is, if you've got a category, you've got those 3 categories, and and do we do 2 categories? It can just, as I say, be 0 or 1 as to which category it's in. But if you've got 3 categories or more, 4 categories, then you can one-hot encode those as 0, 1, 2, 3, and 4. So that is with 3 or more values. The last one is the interesting one. Adding a small number of features that you know are related to what the model is trying to predict, or adding a large number of features that you know aren't related.
So yeah, this is not helpful. Yeah, so
that's not helpful.
Yeah. No. The third is not, because we are selecting not. So third is right.
Oh well, yeah. Sorry.
I also missed the first go. Yeah, because we are selecting the wrong.
Are we happy? Are we happy with our choices? Okay, let's try and check the answers. Yes, pick up the points. Okay, so we'll finish that today then, and come back tomorrow. Sorry, Monday. Monday. And we will be moving on to, we've done our summary there. What's good data? Thinking about something good about unlocking a module. Explore and analyze data with Python. Yes, good. Let's carry on with that on Monday. So have a nice weekend, Ritu.
Thank you. You too. Bye-bye.
Bye-bye.
Bye.
Hello, Steve? Hello?